Today we are going to talk about p-n junction diodes. In this lecture, we will consider a uniformly doped p-n junction. We will discuss the creation of a space charge region. We will determine the energy band diagram of a p-n junction under thermal equilibrium. Thermal equilibrium means we are not applying any voltage. And then we will apply Poisson's equation to determine the electric field in the space charge region or in the depletion region. And we are going to calculate the built-in potential barrier as well. Further, we will analyze the changes in the p-n junction under the application of a reverse bias voltage. And we will derive the expressions for space charge width and for the depletion capacitance. And finally, we will analyze the voltage breakdown characteristics of a p-n junction diode. And towards the end of the lecture, I'm going to assign you some problems. This assignment would help you having a lot of practice of these basic equations, and you would get familiar with a lot of terminologies, some basic parameters that you would need to remember for your exam as well. So this lecture is crucial for you. Formation of a p-n junction. How do you form a p-n junction? You form a p-n junction by placing together an n-type material next to a p-type material. Let's first talk about the n-type material once again. We covered it in the previous lecture, but it's related to the concept of donors. One kind of donor as an n-type material would be, for example, phosphorus. It has 5 electrons in its outer shell, and when it forms covalent bonds with silicon in the crystal lattice, 4 of its electrons would form covalent bonds with adjacent silicon atoms, but then there is a 5th electron which the phosphorus atom can easily release into the crystal. And when it releases that electron into the crystal, this electron can now easily move around into the crystal, but it's going to leave behind it releases an electron, so it's going to introduce a positive charge on the phosphorus atom inside the crystal lattice. So basically, the introduction of donors after releasing the electrons introduces positive fixed charges inside the crystal lattice. Now let us consider the example of boron doping of silicon. Boron is a trivalent impurity, which means it has 3 electrons in its outer shell. These 3 electrons would form bonds, covalent bonds with adjacent silicon atoms over here on the left side and also on the bottom side. But then this place over here, this part, you can see this part, it's broken. It does not form any bond because boron does not have a 4th electron. But there is a possibility for the adjacent atom over here, for an electron in the adjacent atom, to jump from this place over here and fill this spot. So in that case, it's the bond requirement for this atom would be fulfilled, but now we have a missing electron over here, which means that this additional electron would introduce a negative charge on the boron atom, and it's going to leave a hole in the neighboring or adjacent silicon atoms. And similarly, the process repeats, so the hole moves around inside the crystal lattice. But the key point to remember for the sake of this lecture is that after this electron jumps into this part to fulfill the bond requirement for boron, it introduces a negative charge on the boron atom. So the introduction of boron introduces fixed negative charges inside the crystal lattice. Now let us look at it at the cross-sectional view of the p-n junction. Consider the p-type material on the left side and the n-type material on the right side. So as I already told you that the introduction of phosphorus after releasing electrons would introduce fixed positive charges inside the crystal lattice. You can see these fixed positive charges, and then it's going to have plenty of electrons moving around inside the crystal lattice. The electrons are represented by the filled circles, as you can see over here. We have electrons and we have fixed positive charges, but the net charge in this region would be 0. Similarly, talking about the p side, the introduction of boron would introduce fixed negative charges inside the crystal lattice. And similarly, we have majority carriers, which are holes, on the p side of the semiconductor. The holes are represented by open circles. Now you can see that we have high concentration of electrons on the inside and high concentration of holes on the p side. So because of the concentration gradient, electrons would flow from the n-type semiconductor into the p-type region. Similarly, the holes would move from the p-type region into the n-type region. So as you can see that in the region adjacent to this junction of the p and n-type material is called metallurgical junction. Adjacent to the metallurgical junction, we have uncovered positive charges, fixed charges, and uncovered negative charges on the p side of the semiconductor material. And this region is called the space charge region or the depletion region. And because of the separation of charges, we have an electric field, and its direction is from positive towards negative. So basically, in this lecture, we would try to calculate a few parameters. The first parameter, there could be multiple parameters, but whenever we have separation of positive and negative charges, it's going to introduce an electric field, and it will have some built-in potential or voltage, and also we would determine this depletion width or the width of the space charge region. In thermal equilibrium means we are not applying any voltage. Under that condition, we see we have fixed positive charges on the inside and fixed negative charges on the p side. Because of the concentration gradient, the diffusion force tries to force the electrons to move towards the left. Similarly, the diffusion force forces holes to move towards the right. But after this built-in electric field, the diffusion force and the electric field at both edges of the depletion region balance each other. So no more electrons would move into the p-type region and no more holes would move towards the n-type region. And at that point, we have a fixed depletion width or a fixed space charge width. Now let us try to build the equilibrium energy band diagram for the p-n junction. Let us first consider them independently, not connected together. So independently talking about the p-type semiconductor, we know that for a p-type semiconductor, the Fermi level would be close to the valence band. EC represents conduction band, EI represents intrinsic energy level, and it's not an intrinsic semiconductor. Intrinsic means if what undoped. In this case, it is a doped semiconductor, but the intrinsic energy level is represented just as a reference. Mostly it's close to the middle of the band gap in a semiconductor. Similarly, the Fermi level is adjacent to, next to, close to the valence band of the semiconductor, and it's a p-type material, which means that it's going to introduce acceptor levels close to the valence band of the semiconductor. So the key point is, in a p-type material, the Fermi level is close to the valence band of the semiconductor. Similarly, talking independently about the n-type semiconductor, in n-type semiconductor, the Fermi level would be close to the conduction band in the semiconductor. Now what happens if we form the p-n junction, when we bring the p-type layer and the n-type layer next to each other? So when we connect the P and N type materials together, when we bring them together, in that case the Fermi level would be constant throughout the semiconductor material under thermal equilibrium. You need to remember this condition, that for a p-n junction the Fermi level would be constant throughout the material under thermal equilibrium when a voltage is not applied. Okay, so then once again we know that the Fermi level would be close to the valence band on the p side of the semiconductor, and similarly it's going to be close to the conduction band on the inside of the p-n junction. Now how about connecting the conduction band together in the middle? How do we do that? So as you can see over here, now we connect the conduction bands on both sides together, and you can see this curvature. You cannot connect them with the help of a straight line. It has to have this kind of curvature, and I'm going to tell you later why do we have this curvature when we perform some calculations for in order to determine the voltage of the semiconductor in the depletion region. So once again we have the same energy band diagram under thermal equilibrium, which means zero applied bias. You can see we have a constant Fermi level throughout the semiconductor. In the intrinsic Fermi level stays in the middle of the energy band gap. We have the conduction band and we have the valence band. Now, talking about the movement of electrons from the N side to the P side. Electrons try to settle down at the bottom of the conduction band. So most of the electrons would be accumulated in this region over here. They cannot cross over to the p-type region, because if they have to cross over to the p-type region, they have to cross over this barrier. Similarly, talking about holes, holes also face a barrier in order to move into the inside of the p-n junction. Holes are just like bubbles. Bubbles try to go to the top, to the surface of water. So similarly, holes try to stay at close to the maximum of the valence band. So holes are going to be trapped over here. And this potential, the difference between the conduction band on the N side and the conduction band on the P side, it's called the built-in potential, represented by VBI. Similarly, the built-in potential is the same on the for the valence band as well. This difference between the valence band on the P side to the valence band on the N side. Another parameter is called the Fermi potential, represented by phi Fn, Fermi potential on the N side, and it's the difference between the intrinsic energy level and the Fermi energy level. Similarly, phi Fp is the Fermi potential on the P side of the semiconductor, the difference between intrinsic Fermi level and the Fermi level. And the sum of these two, if you measure them and add them together, the sum of phi Fp and phi Fn is equal to VBI, the built-in potential. Now, you might see that there is this E is multiplied with VBI and also phi Fn and phi Fp, because the energy band diagram is represented in the form of energy. EC, EFI, EF and EV, all of them, they represent energy, while VBI has a unit of volts. Similarly, phi Fn and phi Fp, they also have units of volts. So you multiply them with the charge on electron to convert them into energy, and its unit would be electron volts for this entire parameter. Similarly over here and also over here. Okay, we already talked about this slide. Excuse me. Now the goal over here is to calculate the built-in potential, this barrier. And in order to calculate the barrier, we know that VBI is equal to the sum of phi Fn and phi fp are the sum of the magnitudes of the Fermi potential on the n side of the semiconductor plus the Fermi potential on the p side of the semiconductor. And N naught represents the carrier concentration in the n-type semiconductor under thermal equilibrium. Nc is the density of states in the conduction band. Exponential of minus Ec represents the conduction energy level, and Ef is the Fermi potential, K is the Boltzmann constant, and T represents temperature. KT basically represents thermal energy. Its unit is 0.026 or 26 millielectron volts at room temperature. So this equation, the carrier concentration or electrons concentration in the n-type semiconductor can be calculated using this equation, and I don't want to go into the details of the calculation because in order to understand the details of it, we would need to cover like 2 more chapters, and it's not really required a lot for today's lecture, so I don't want to go into the details, but anyhow you can calculate N naught using this equation. N naught can also be calculated in another way, is equal to Ni, the intrinsic carrier concentration of a semiconductor. Intrinsic carrier concentration means the carrier concentration or the electrons and holes concentration in a semiconductor when it is not doped. So let me ask you a question, and you will have to deal with this number again and again, so that's why I'm asking you. What is the intrinsic carrier concentration for silicon at room temperature? Well, it's fine if you don't know. The intrinsic carrier concentration for silicon at room temperature is 1 into 10 to the power of 10 per centimeter cube, which means even if it is not doped, we would still have 1 into 10 to the power of 10 electrons per centimeter cube for the semiconductor. So Ni represents the intrinsic carrier concentration, Ef is the Fermi level once again, and EFi represents the intrinsic Fermi level. Now Ef minus EFi, or EFi minus Ef, can be represented by phi Fn, E phi Fn, the Fermi potential on the inside of the semiconductor. So replace this value into this equation, you get, it's going to result in this equation, and after you reorder this equation in order to determine phi Fn. So in the next slide you can see phi Fn can now be represented by this equation. Similarly, we can repeat the same process for the concentration of holes on the p side of the semiconductor, and then replace EFi minus EF with phi Fp over here. EFi minus EF, replace it with phi Fp, and then after some reordering you can represent phi Fp in terms of Na, which is the acceptor doping, divided by Ni, which is the intrinsic carrier concentration. And Vbi, as I already told you, is the addition of the magnitudes of phi Fp plus phi Fn. Vbi is equal to phi Fp plus phi Fn. And then insert the values of phi Fn and phi Fp in this equation. Here is the final form for Vbi. Vbi is equal to Kt by Q. Kt by Q is thermal voltage. Its unit is 0.026 electron volts, or 26 millielectron volts. Well, excuse me for a minute. I got to sign a form. Right. Getting back to the built-in potential, so built-in potential is equal to kT by Q, 26 millielectron volts, natural log of Na Nd divided by Ni square. Na represents acceptor doping, Nd represents the donor doping in the N-type semiconductor, Ni is the intrinsic carrier concentration. Or you can replace kT by Q with Vt. Its unit once again is volts, and its value is 26 millielectron volts. This is an important equation for you. Towards the end of the lecture, I'm going to assign you some problems, and in those problems you will have to calculate the built-in potential. Now, the built-in potential means that in order to overcome this barrier, you have to apply a certain voltage, which is represented by VBI. And the built-in potential is directly proportional to the acceptor doping for the p-type semiconductor, to the donor doping for the n-type semiconductor, and it's inversely proportional to the intrinsic carrier concentration for silicon. So if you increase the acceptor and donor doping, the built-in potential would be higher, and if you decrease the doping concentrations, the built-in potential would be lower. Let us try to calculate VBI with the help of an example, try to understand it. The question is, calculate the built-in potential in a PN junction. Now consider a silicon PN junction at T is equal to 300 Kelvin. 300 Kelvin is basically the room temperature with doping concentrations of 2 × 10⁻17 per centimeter cube and donor concentration of 10⁻15 per centimeter cube. Now we are required to calculate the built-in potential. VBI is equal to this equation. Replace the value of the thermal voltage in this equation, natural log of, and then the acceptor doping, the donor doping, Ni intrinsic carrier concentration, as I already told you, it's roughly 1.5 × 10⁻10 per centimeter cube at room temperature for silicon. So you got to remember this value. And the built-in potential is 0.713 for these levels of doping concentrations. Now what happens if you decrease the doping concentrations? Like for example, consider the donor doping concentration of 10⁻15, which is the same as in the previous case, and now replace the acceptor concentration with 10⁻16 per centimeter cube. So if we reduce the doping concentration and then calculate the built-in potential, now the built-in potential is 0.635 volts for silicon at these values of carrier doping concentrations. Generally, the built-in potential for silicon is in the range of 0.5 to 0.9 volts. Do any of you remember the band gap of silicon? What is the band gap of silicon?
Uh, 1.12 eV.
1.1, roughly 1.1 electron volts. That is right. So generally, the built-in potential is closer to the band gap of the semiconductor. Like for example, for silicon, the built-in potential roughly on the average we can say it's 0.7 volts. It's in the range of 0.5 to 0.9 depending on the doping concentrations, but roughly it's 0.7. We say to average it out, it's 0.7, which is close to the band gap of the semiconductor. The band gap is 1.1 electron volts. If you consider another semiconductor, for example, gallium nitride, the band gap of gallium nitride is 3.4 electron volts, and the built-in potential for gallium nitride is approximately 3 volts. So the built-in potential generally stays close to the band gap of the semiconductor. It's also called the turn-on voltage for diodes. Now we calculated the built-in potential. How about the electric field of the semiconductor? So to determine the electric field, we have to apply Poisson's equation. Poisson's equation, here is Poisson's equation in 1D. The derivative electric field is equal to the charge density in coulomb per centimeter cube divided by the permittivity of the semiconductor material. And by using this equation, we can determine the electric field for the p-n junction. Now the charge density for the p-n junction is represented in this form over here. On the inside of the semiconductor, we have positive charges, and plus xn represents the edge of the depletion region on the inside, or in going back to the previous slide, right? Yeah. So here is the charge density in coulomb per centimeter cube. Plus xn is the edge of the depletion region on the inside of the semiconductor. Similarly, minus xp represents the edge of the depletion region on the p side of the semiconductor. And we have positive charges over here. So the charge density would be E and D on the inside of the semiconductor, and minus E and A on the P side of the semiconductor, because on the P side we have negative charges. And A represents the acceptor doping, and D represents the donor doping. And then basically, let us go to this. Electric field is the integration of the charge density, basically looking at this figure. Now here we have a constant number, and even on this side we have a constant number. What is the, so if this is some constant, for example 1, what is the integration of 1?
0. Maybe x.
The integration of 1 is x, which represents a positive ramp, right? Similarly, what is the integration of minus 1 would be negative x, right? Which represents a negative ramp. So this is how we calculate the electric field. Now how do you calculate the voltage across the depletion region? The voltage is the integration of the electric field then. So what is the integration of x?
X square by 2.
X square by 2. So there is you get like a parabolic representation. So for the positive, we have this curvature, and then for the negative we have this curvature. So let us go to the next slide now. Alright, talking about the calculation of the electric field. So how do you calculate the electric field? You have this Poisson's equation. In order to calculate the electric field, rearrange the equation in this form. Calculate the electric field by integrating the charge density. In charge density, rho of x is E and A. So electric field is equal to minus E and A divided by ES into x plus C1. And the constant of integration is determined by setting electric field is equal to 0 at x is equal to minus xp, like at the edges of the semiconductor. So let us go back to this figure. We have electric field because we have separation of positive and negative charges inside the depletion region, but the electric field would be 0 in the neutral regions, for example in this region and also in this region. And the edge of the depletion region on the p side is represented by minus xp. So below minus xp, the electric field would be 0. So by setting E is equal to 0 at minus xp and replace x with minus xp, set E is equal to 0 in this equation, you find the constant of integration and replace the constant of integration into this equation once again. We get the equation for electric field, which is minus E, charge on electron. You need to remember the value of charge on electron as well, which is 1.6 into 10 to the power of minus 19 coulomb, times the acceptor doping into x plus xp. xp represents the edge of the depletion region on the p side, and x could be any value between minus xp to 0. X ranges between minus xp and 0. Similarly, epsilon s is the permittivity of the semiconductor. It's the product of the relative permittivity, which is 11.7 for silicon, times permittivity of free space, which is 8.854 10 to the power of minus 14 farad per centimeter. So we calculated the electric field in this region between minus xp to 0. We can repeat the same process to calculate the electric field between 0 to xn. So we got a representation for electric field between 0 and xn as well, and here is the equation. Xn once again is the edge of the depletion on the inside of the semiconductor. All right. So you get a negative ramp for electric field on the p side of the semiconductor and a positive ramp for electric field on the n side of the semiconductor. Looking at this plot, where do you think the electric field has the maximum value?
0.
At x is equal to 0, which is also called the metallurgical junction. So at x is equal to 0, it has the maximum value, and once again this equation and the equation given in the previous slide, it will have the same value. So equate this equation with this one at x is equal to 0, and then you get this equation in A xp is equal to nd xn at the metallurgical junction. It's a useful equation. In A is the acceptor doping, xp is the edge of the depletion region on the p side of the semiconductor. Similarly, xn is the edge of the depletion region on the n side of the semiconductor, and d is the donor doping. So for the p-n junction, if you in this equation, if you know any three values, you can calculate the fourth one. For example, if you know in A xp and xn, you can calculate the value of nd. Similarly, for the other parameters as well, if you know three parameters, you can calculate the fourth one. So this is a really useful equation. Now, moving on to the next slide. We calculated the electric field in the depletion region. Now, how about calculating the voltage in the depletion region? And previously, we calculated the built-in potential, but the built-in potential is edge to edge in the entire depletion region. Now, we want to have an equation for voltage at any point in the depletion region. How does it look like? So voltage, basically you can calculate it by integrating the electric field. What is the unit of electric field? Does anybody know the unit of electric field? The unit of electric field is a volt per centimeter, or basically electric field is equal to voltage divided by distance. So in order to calculate the voltage, you just integrate the electric field. So I mean the calculation process is lengthy, but here are the resultant equations. Here is an equation for potential between 0 and xn. As you can see, it's a longer equation, xn, x, everything I already told you about. And then for the p region, here is once again the equation for calculating the potential at any point in the depletion region between minus xp to 0. How about VBI? Once again, what is the built-in potential? The built-in potential is the potential at x is equal to xn. So if in any of these equations, if you replace x with xn, you get this equation E divided by 2Es ndxn square plus Na xp square. So now to calculate the built-in potential, there are two ways you can calculate it. One way I already told you is this equation, VBI is equal to KT by Q natural log Na nd divided by Ni square. And another way is using this equation, E divided by 2Es ndxn square plus Na xp square. Now, how do you calculate the depletion width or the width of this region between minus xp to plus xn, edge to edge depletion width? In order to calculate that, I already told you about this equation. Reorder this equation for xp is equal to ndxn divided by Na, and we know the value of VBI as well. So then in this equation, replace xp with this value, and by reordering you get an equation in order to calculate xn, which is the distance between the metallurgical junction to the edge of the depletion region on the inside, or the depletion width on the inside of the semiconductor material. Similarly, the depletion width on the p side of the semiconductor can be calculated using this equation. And how about the total depletion width? So if you have already calculated the depletion width on the n side and the depletion width on the p side, just add them together. And if you have not done that, you can just replace the values of xn and xp in this equation, and here is your final form for calculating the depletion width of the semiconductor. 2 times permittivity of the semiconductor times built-in potential divided by charge into acceptor doping plus donor doping divided by acceptor doping times the donor doping, and take the square root of everything. So basically you got equations for calculating the built-in potential, the electric field, the potential inside the depletion region at any point, and for the depletion width of the PN junctions. Now let us try to understand it with the help of an example in which we are given calculate the space charge width and the electric field in a PN junction for zero bias, which means under thermal equilibrium. So whenever you see zero bias, it means under thermal equilibrium. Consider a silicon PN junction at room temperature, and the donor and acceptor dopings are given. So we got to calculate the depletion width, and we have equation for this is the equation for depletion width. The acceptor doping and the donor dopings are already given, right? We know the charge on electron 1.6 10 to the power of minus 19 coulomb. The permittivity of silicon is 11.7 8.85 10 to the power of minus 14 farad per centimeter. But we have to calculate the built-in potential, and the built-in potential is calculated using the previous example, using this equation. Acceptor doping is given, donor doping is given. Intrinsic carrier concentration for silicon we already know at room temperature has this value. And here in the next example, the acceptor and donor dopings are these ones. So the built-in potential is 0.635. Right, replace the value of VBI and all the other values, and now the space charge width is 0.951 10 to the power of minus 4 centimeter, or 0.951 micrometers. So this is the width of the depletion region, and this is the total width. But you can also calculate the width of the depletion region on the N side and the width of the depletion region on the P side. The width of the depletion region on the N side is 0.86, and the width of the depletion region on the P side is 0.086. I want to show you a relationship between the doping concentration and the depletion width. So which of the depletion widths is higher, Xn or Xp? I mean, you have the values, right?
Xn.
Xn is higher. How about the acceptor and donor concentrations? Which one is higher? It's given in the problem statement. Which concentration is higher, acceptor or donor?
Acceptor.
The acceptor concentration is higher. The acceptor concentration is higher, but the depletion width on the P side is lower. What does that mean?
Higher concentration will give a smaller depletion region.
That's true. Which means that there is inverse relationship between the doping concentration and the depletion width. Since here the acceptor concentration is higher, the depletion width on the P side is lower. Similarly, the donor concentration is lower, so the depletion width on the inside is higher. And there is a technical reason for that. If the doping concentrations are higher, the fixed ion charges would be confined in a smaller region, so that's why the depletion width would be lower. But anyhow, there is inverse relationship between the doping concentration and the depletion width. The peak electric field at the metallurgical junction so then we have an equation. We are asked to determine the electric field as well, and the peak electric field at the metallurgical junction is given by this equation. The equation is already given in the previous slides. Alright, so here is the equation for the electric field. Now the peak electric field would be at the metallurgical junction, right? So just set x is equal to 0 in order to determine the peak electric field. So peak electric field is equal to minus E and D divided by ES xn, or there is also another equation, or minus E and A divided by epsilon S xp. So you can calculate the peak electric field with either of these two equations. So in this problem we are asked to determine the maximum or the peak electric field. Just use this equation. We have the value for xn and d, the charge on electron, and es is a material parameter. So the peak electric field comes out to be minus 1.34 10 to the power 4 volt per centimeter. The modes of operation of a PN junction. Right. Let's have a break of approximately 15 minutes so that I can save the previous recording, and then we will reconvene at 1 p.m. All right.